Hello everyone, this is Chris Wells, and welcome to the first video of 3, where I will be explaining how to complete the vector extra credit opportunity for Anke Huscher's trigonometry class. If you are interested in this project, please send me an email at cwells9@student.yosemite.edu, cwells9@student.yosemite.edu. And say something like, "Hey, this is so and so, and I'm interested in the project. I'm interested in getting some extra credit for trig," um, and I will respond to that email with some information and some access to things. I will give you access to this Google Docs, in which I would like you to put your name next to any of the buildings that you want to um, provide information for. Now, do not choose the reserved because I'm using those for demonstrations. For your class, I'm using Tamarack Hall as um, a demonstration for the vectors. I have been using not Sequoia. I've been using Manzanita as an example for the meetings through the STEM Club. But when you pick a building, you're going to be getting information. So there's going to be 3 geographic points that I want you to obtain. Number 1 is the origin point, which I have already given you. I want everyone to have the same origin point for sake of consistency. But the base point and the tilt point, I want you to choose. I have 2 rules for the base point and tilt point. The first rule is that it needs to be on an exterior wall, and that wall needs to be flat. So it needs to be a straight wall, not a curved wall. And they both the base point and the tilt point need to be on the same section of wall. So how do you get all these points? How do you get the locations for them? You go to a website that I will be providing the link to in my email response. This make sure you're using Firefox or Chrome. But this is a really cool website. Cores Map gives you data for many, many different data points, data access points throughout the entire world. And the cool thing is, we actually have a data access point on campus. Professor Jeff Tolhurst here on campus, he does GIS and geographic surveying and drones and a bunch of other cool classes. And he's also one of the faculty, I don't even know what you call them, faculty advisors, faculty administrators for our STEM club. So he has told me about this. He is a huge supporter of this project, and he has told me about this website. He has given me access to it. This is a really cool website because it, as you see, if I zoom out a little bit more, it's a little bit laggy, and I don't know why. But if I zoom out, see, it gives you some elevations, but it also gives you the latitude and longitude of where your cursor is. And here's the way it does it. So if I zoom out all the way, well, maybe not all the way, but if I zoom out, there's a lot of points here on the map. And basically, it says the 3 nearest points, and it has no idea where your cursor is on the map. So I should back up and kind of think about, kind of explain the theory of maps for a little bit. So Earth is approximated with a sphere. Earth is round, but paper maps are flat. So there's actually a really big mathematical problem when you're trying to convert a sphere into a rectangle. Not only are you losing an entire dimension of data, but you're also limited on how to represent that data and how to approximate it. So there is no good way to relate my cursor as it's moving around in the middle of the Pacific Ocean here to exact locations in latitude and longitude because of the way that spherical coordinates are converted into linear coordinates. So here's what they do instead, is that we have precise locations for every single one of these data points. And what it does is it picks the nearest 3 and it triangulates the position. So that's exactly what's happening here with the cursor. Is it triangulates the position. And as you saw before, they actually have some buildings on campus already. But the cool thing is that they actually have some of these floor plans. So I actually know where these walls are relative to everywhere else. And that's kind of the information that you're going to need in order to pick a base point and a tilt point. Like I said, they need to be on an exterior wall. And for this video, well, actually for these 3 videos, I'm going to use Tamarack as an example. So I chose this top left corner to be the base point, which is what that means up here. It's the top left corner. I guess I should specify it's the corner, and the top right corner as my tilt point. So the base point goes from this origin point over here. This right here is the origin. And from there to here is going to be what I'm going to have you guys call the direction vector. From here to the tilt point, which I put as the top right corner, which is right here, is what I'm going to be calling the prime direction vector, or D prime for short. So what we have is we have a location for our origin, we have a location for our base point, we have a location for our tilt point. And like I said earlier, this is actually a map. So it's 2-dimensional. It's not 3-dimensional. It's not on the Earth itself. And to kind of show some of the differences, I'm going to go over here and show you what it really means to have a vector in spherical coordinates. A spherical vector is a vector that is really just a line that curves around. It's think of the path of an airplane is actually just a vector on Earth, a real spherical vector. And as you see, these spherical vectors are round, but that actually comes up with a significant problem because AutoCAD, as well as this program right here, as well as SketchUp and a few of the other programs that we're going to be using to model and export the campus, they are not in spherical coordinates. They are in X, Y, and Z, which is a length in the width, a length in the length, a length in the length, and a length in the height. So it's a width, length, and height coordinate system, not a latitude, longitude, and global radius. This is actually a big problem. So if this is my base point here on Earth, and this is my base point, and sorry, if this is my origin point on Earth, and this is my base point, and this is my tilt point, then these would represent the actual vectors that go around in this coordinate system. But I don't want that coordinate system. I need it to be in X, Y. So I'm going to jump into CAD to explain kind of the diagram here. If these two numbers look familiar, it's because these numbers were found here. So they were actually the coordinates that I used to find the base point and the tilt point, and I put them down here. So after you've picked your building or buildings, plural, make sure that you put your base point location, a brief description of where it is. That description pertains to the cores map. So it's the top left corner of the cores map of Tamarack on the cores map, okay? And do the same thing with your tilt point. And leave this information here. And then I will go into this file every now and then and see the progress. And then I will take these two, I will look at this information, and then I will go into my CAD file and I will look at the building that you have selected. So this is actually Tamarack. This is this is the bottom story of Tamarack. And this right here is the base point. And this is the tilt point. It just so happens that it's also the top left and the top right, but it does depend on the CAD file and where it is on the cores map. But what I have done is I have taken those 2 points and I've calculated the distance between them in CAD. It's 136 feet from here to here. And again, it's laggy for some reason. So I have converted that into metric and it represented it in meters form here. So 136 feet is 41.4528 meters. And the reason why I've done this is actually, um, it's very important. When I'm looking for data here, I'm actually looking for data in kilometers because it says everything in here is in kilometers. The way that we count latitude, this latitude and longitude coordinate system is it's all in metric. These are not um, feet and inches and miles distances. These are in kilometers and meters. And so I need to be able to convert. I need to convert all of my building data, which is an imperial, to the metric cores data in order to work with the same units. Now, another reason why I have um, converted into uh, metric from the data that I got over here is because I need it to be a higher accuracy. This is what it is in meters. But notice that the cores map has everything in kilometers. So 0.33 kilometers is 330. So right here it says that the base point is about 0.3 kilometers, 0.34 kilometers. That's 340 meters. That means that if I were to use this CORS website for distances, I'm going to get the wrong distance. I need to have a higher accuracy because I need to put it in an AutoCAD much greater than the nearest 10 meters, which is the nearest 27 feet or something. I need an accuracy much smaller than 27 feet. So this is why I need some of the vector information that you guys will be calculating, because you're going to calculate the magnitude of the direction vector and the magnitude of the direction prime vector. I will give you the magnitude of the tilt vector. And what you're going to do by calculating here is you're going to take the exact latitude and longitude coordinate of this point, which I have provided in here as the origin point, and you're going to calculate the great circle distance between this point, and then use that great circle distance as a linear separation. In other words, you're going to take the distance between this point on Earth and this point on Earth and represent it as a straight line, as a vector. So, whoops, where is it? So this is kind of the idea. These two are your direction vectors. These two yellow lines are your direction vectors, and this cyan line is your tilt vector. So if I were to delete what I have over here, the idea of the direction vector is it tells me the location of the building relative to where the origin is. But there's a big problem because this thing is a base point. It's not a base building, it's a base point. In other words, it's only telling me information about this one point right here. Notice that all the other points can rotate and still make this statement true. The statement is that this vector represents the distance from the origin, which is here, to this point right here. But it isn't until I add a second vector that I'm able to accurately represent this information. And I add a second vector, this one, like this, and I calculate the difference between these two vectors, and that's the cyan vector. And I better make sure that that cyan vector's magnitude is the same as this. In other words, use this as the magnitude because that's what I'm giving you as the actual magnitude. I will reply back to that email, or I might put it in the Google Docs sheet. I haven't really decided yet. But now that this has two vectors on it, there's only one possible way that I can move this building such that this vector points to this location and this vector points to this location. This is the only possible way that I can represent it. There's no more rotation. So to recap, I need a direction vector, a primal direction vector, a tilt vector, that I'll give you the magnitude for, so I can figure out the position and the orientation of any building on campus. So there's one last thing I'd like to go over, and it might be something you've already noticed. Notice that there's a lot of buildings on this list, and not every one of those buildings is on this map. Well, that's because um, there really isn't all the buildings on the map. You can choose. I'm giving you permission to choose any of the buildings on this list. If you choose a building that someone else in your class has already chosen, then as far as I'm concerned, the only person that's going to get credit for that is the person with the highest and most reliable accuracy. So if 3 people chose Oak Pavilion, then only one person is going to get maximum credit for that extra credit opportunity because that person has the highest accuracy. Okay, so this is kind of to encourage people to choose different buildings, so I don't get a bunch of Oak Pavilions, Red Buds, and Sequoias, because those are easier buildings to do. Um, and number 2 is if you choose a building that is on the list but it's not on the map, as far as I'm concerned, and I'll have to double check this with your teacher, but as far as I'm concerned, that is a lot more work. It requires more work to calculate the vector for position and orientation without knowing where it is on the map. And the reason why is because you need to triangulate that coordinate position. I will explain how to do that in the 3rd video. But for now, I think this is a good introduction to what I want and what I'm asking for. Anka Husher, Professor Anka Husher, has requested that each person who wants to do this must choose at least 2 vectors. Because each building requires 2 vectors, then each person who wants to do this must do at least one building to get full extra credit. Again, I'll have to talk to her about getting extra credit for buildings that represent a significant challenge to find the position of. But for now, look out for the 2nd video. Thanks for watching.